And I'm interested in quantum computing, so different topics such as quantum algorithm for problem in optimization, statistical estimation, quantum complexity theory, so lower bounds in different computational models such as query complexity, space complexity, communication complexity. And recently, I have also started to be interested in post-quantum cryptography. So in this presentation, I would like to give you a brief overview of some of the work I did on statistical estimation. And if I have time, I will move to a second topic, which is about space complexity. So those are unrelated questions. Okay, so let me start with this work on statistical estimation, and it's about the mean estimation problem in the one-dimensional case over the reals. It's a very standard problem in the classical setting, which is pretty well known. And the setup is defined as follows. You have some unknown distribution D specified by some probability vector. And this distribution is obtained as outcome of some experiment. Okay, this experiment can be classical, quantum. I mean, I will explain later on what is a possible input model. And so this distribution, so this is a possible example. It has some mean mu, and I will assume it has a finite variance. And so there is a natural complexity parameter, which is a number of times you can repeat this experiment to obtain information about this distribution. And in the mean estimation problem, the goal is to process those information in order to compute an estimate of the mean mu. Okay, so this estimate denoted by mu tilde, you want it to be as close as possible to the mean. And the standard error bound that you want to satisfy is shown here in red. You want to find the smallest error term, which is the distance between mu and mu tilde. And you want it to hold with probability 1 minus delta. Okay, so this is really the standard mean estimation problem. Now let's see a few possible models to study this problem. I mean, how do we define an experiment? So the first model, which is the classical one, in this case, an experiment is just a way of obtaining one sample from the input distribution. Okay, so you can, if you perform an experiment, it means you obtain n independent samples. A second model, which is of a quantum nature, consists of having a quantum state called a quantum sample, which is just a coherent encoding of your distribution. Okay, so in particular, what you can do is you can measure this quantum state in the standard basis, and you would obtain a classical sample. So this model is at least as powerful as the previous one. And the last model, which is even more powerful, consists of having access to a quantum circuit such that it prepares a quantum sample if you apply it on some fixed basis state. Okay, so you have a black box access, meaning you can apply this circuit on any state of your choice. So now the natural question is, what is the best error bound we can obtain in each of these three models? And first, in the classical setting, the answer is pretty well known. The best you can have is on the order of the standard deviation of your unknown distribution, divided by the square root of the number of samples you are getting. Okay, and the estimators that satisfy this bound are called sub-Gaussian estimators. And there are many possible choices for those estimators. Maybe the most well-known one is the median of means. Now, if you move to the second model, which is like a quantum input model, it turns out that you cannot do better than in the previous case, meaning the best you can do is just to measure those quantum samples to obtain classical samples, and then run a classical sub-Gaussian estimators. There is no speed up at all in this setting. And the last model, which is the most interesting one for people doing quantum computing, for those kind of questions, it turns out that it indeed allows you to obtain some advantage in the quantum setting. And more precisely, one can show that you can achieve a better scaling in terms of the dependence on n, the number of experiments, which is linear instead of being the square root of n. Again, it's optimal. So obtaining this bound is not as easy as it may seem. I mean, classically, it's pretty simple. I mean, if you don't care about constant factor, you can just apply the median of means. But quantumly, it's a bit more complicated, and there have been a long series of work to obtain this bound. I mean, starting more than 20 years ago. And in particular, the dependence on the standard deviation was complicated to obtain. I mean, some of those estimators do not perform good if the distribution is heavy-tailed. Yes?
Do you get access to the inverse of U as well?
Yeah, you also have access to the inverse of U. Yeah. Okay, and I mean, those works culminated in this optimal dependence on the standard deviation. So I'm not going to explain how those quantum mean estimators are designed. I just want to give you a brief idea of the techniques that are used for those kind of algorithms. And those techniques lie at the intersection between quantum algorithms and statistics. So on the quantum algorithmic side, people use like phase estimation, quantum counting, amplitude amplification to perform those kind of mean estimation. And those techniques are combined with methods such as like outliers detection or trimmed estimators. Okay, so it's a really interesting area where you have to like combine those two different topics together. And there are many interesting open problems which are related to those questions. I mean, maybe one of the most interesting one is to look at the high dimensional setting, for which there is not much which is known in the quantum setting. And there are other questions like the robustness of quantum mean estimators, or like application in statistical physics for estimating partition function, application to the Monte Carlo method, etc. So I would be interested to talk with you about any of those open problems if you are interested in. So I think I have time to move to the second part. Okay, so this is about different research areas that I also find interesting, which is unrelated to the previous one. So this time it's about complexity, so like proving lower bounds. It's not about finding algorithms. It's a particular type of complexity result in which you look at what can be done or what cannot be done when you have a small quantum computer, I mean, a small memory algorithm. Okay, if the memory is limited, can you still do some useful tasks? So this is an interesting question, in particular in the quantum setting, because we expect to have small quantum computers in the near future. So being able to understand the power of those computers is important. And the way this question can be addressed is by looking at trade-off lower bounds, which consist of studying two different complexity parameters at the same time. So for instance, you could look at the space versus the query complexity, and you could ask a question such as, if I have a limited amount of memory, how many quantum queries do I have to perform on my input to solve some problem of interest? Okay, is it like more quantum queries than in the unlimited memory case, for instance? A second kind of trade-off is sample versus space complexity. So again, the sample complexity increases when the space is limited. And another possible trade-off is communication complexity versus round complexity. So I worked a bit in the first setting, the space versus query complexity setting. And with my co-authors, we looked at a trade-off for the problem that consists of finding many collision pairs in a random hash function. Okay, so there are quantum algorithms that obtain like speed up for solving this problem. However, if you look at those algorithms, they need a huge amount of quantum memory. And so we ask the question, the following question: if you have a small quantum memory, do you need more quantum queries? And it turns out that the answer is yes. I mean, this problem of finding many collision pairs, indeed becomes more difficult to solve in the small memory setting. So there's still open question, around this topic, and probably there is still a gap between the lower bound and the upper bound, which has to be closed. A second result, which I find interesting, and which you probably already know of, is about a result by Ranras obtained a few years ago for this second setup of space versus sample complexity. So it's about the classical setting. So we have a classical computer, and the goal is to solve the so-called parity learning problem. And what Raz showed is if you have a small memory, this problem has an exponentially large sample complexity. Whereas if you have a sufficiently large memory, it has just a polynomial sample complexity. And so a natural question is, what if you have a quantum memory instead of having a classical one? And the question is completely open. And it seems to be a really interesting one with connection to quantum cryptography, quantum leftover hash lemma. So it's probably a very interesting research topic. Okay, and again, if you are interested in any of those questions, I would be interested to talk with you. Okay, and with that, I thank you for your attention.
So I have a question. It's related to Raz's work, but not exactly. So, well, suppose you just want to do Gaussian elimination.
Yes, so you can do Gaussian elimination.
Yeah, I know you can do, but the memory. I mean, what is known in terms of quantum memory about how much memory do you need?
Yes, so if you want to solve parity learning over a vector of size n, Gaussian elimination would require n square bits of memory.
Workspace as well?
Yes, workspace in classical. I mean, you need about n samples to do Gaussian elimination, and each of which is of dimension n.
Yeah.
So it's n squared bits of memory in total.
So the parity result, right, says that n squared is enough, but what's the parity result?
So it says that if you are below n squared over like 25 or something like that, so just slightly before n squared, then you need exponentially many classical sample. So the gap is really just about the constant factor. It's a very.
So is it possible that with quantum memory you could do better than this?
Yeah, it could be possible, but we don't know of any quantum algorithm for this problem. And again, in the quantum setting, we are using classical sample. Like if we have quantum samples, there is like quantum algorithm for finding parity efficiently. But with classical sample and quantum memory, we don't know of anything better than Gaussian elimination.
So the question of quantum samples with quantum memory is open.
No, I mean quantum sample, quantum memory is I mean you can solve the problem efficiently.
Okay.
But the question is really about classical sample with quantum memory.
So you can do it better than n squared.
Yeah, so we don't know that.
With quantum and quantum, yes.
Yeah, with quantum and quantum, the answer is yes. You can do better.
How much better?
You can just apply Hadamard transform on your sample.
So n log n kind
of? The memory, I think it's just linear instead.
It's linear?
Yeah, really quick. Is there like a succinct way to state where Raz's result gets stuck when you try to is the lower bound and the memory quantum, what stuff is stuck? Is there
So okay, at the heart of Raz result, there is a kind of a progress measure, which is used to analyze some branching program, which is the model you use in bounded computation. And this progress measure, I mean, turning it into a quantum progress measure, I mean, you have many obstacles, like some data processing inequalities that do not work anymore and stuff like that. So, yeah, I mean, there is apparently no easy way to convert Raz result in a quantum version. But maybe it's
Okay. So next we have Chitan. That's about, I guess.